All right, we're already at day 9 of our environmental data science class, and today we're going to be working with raster data in R. And the project we're going to be working on is sort of reproducing some analysis that the USGS recently has done that looks at topographic change in the United States. So many activities like urbanization or mining change the actual topography or elevation profiles of the landscape, and the USGS wanted to index those by using 2 different elevation map sources. So we'll go ahead and click on this link here, and you can sort of read about this project here, but basically they compare one elevation data set, which is the National Elevation Data Set, which is compiled by the USGS, and another one, which is the Shuttle Radar Topography Mission, which is a satellite that records elevation as it passes over the Earth. And the way we're going to sort of do this is go into their data and tools. We'll look at this topographic change viewer, and you can see what they've done is this basically just a map of all the places where people have changed the elevation enough that it was detected by their analysis, essentially. And there's these little blue and red dots. It's kind of a slow page, and this is sort of why I want to reproduce it in R. But at the top right over here, there's this button for download. And what we're going to do is click that. And then we get this link to this topographic change polygons. And rather than directly download it, I'm going to go ahead and say open link in new tab. I'm going to cancel the download. But what I'm going to do is copy this URL. And that's going to allow us to directly download it in an R script so that if future users use it, they can actually just do this part and not have to point and click their way to where we just were. I've already created an R project for this, and I just call it mining impacts to elevation. And this was I was practicing for this, so we'll go ahead and do new R markdown, and we're going to say topographic change caused by people. We'll keep it as an HTML. As always, delete most of that. And then I'm going to save it. I'll save it outside of a source file for now. We'll say SRTM NED. So that's the 2 elevation data sets. So we're going to say first, analyzing topographic change. So the very first thing we want to do is download the data. We are going to use some key packages that you're going to want to install before class. As always, we're going to start with the tidyverse. We're going to use SF. We'll use mapview again. We're going to add a new package here called Raster. And Raster is the sort of main package for many years that our users have used to analyze raster data. I'm just making sure that this is commented. Okay, so we're also going to add this other really sweet package called Elevator. And what Elevator does is it downloads elevation data sets from the NED directly in R. And the NED is the National Elevation Data Set. Okay. All right, so first we want to make sure we download. We're not going to reproduce the whole analysis of the USGS, so we're not going to download all of NED and all of the SRTM data. We're just going to download data around where they've identified that people have moved the Earth in significant ways. So first I'm going to create a new file, or a new folder, and that's going to be called a data folder. So we can use this command. Instead of going over here and saying new folder, we can actually just use a command called dir create data. And if you pay attention to the right-hand side where the cursor is, when I run this line, dir create data, it's going to create a directory called data filled with nothing. So it just makes sort of creating a new folder easier. You'll notice if I rerun that, I get a warning that it says it already exists. So it's just saying like, hey, I'm not going to create one. You already have one. So that's good. And then we're going to use this command called download file. So if we go download file, we'll have, you'll see that there's a URL. So that's probably the URL I just copied from the internet. And then a destination file. So this is sort of where do you want to put it in your file structure. So let's go ahead and do this. We'll say URL equals, and then put it in quotes. Oops, I copied that out, so I'm going to have to go back and download this again just to get the link. All right, we have that link. The dest file, we want it to go into data. And if we look at the end of the link from the internet, it's a .zip, so we want to make sure we give it the proper assignment. So we'll do data /, so now we're in the data folder, and we'll just say topo change.zip. And now we'll download the file. This little thing should pop up, and you're going to download the file pretty quickly. It's 8.4 megabytes. And then if we want to check that it's there, we can go click on the data and look in there. We could also look to see if the file is there by just saying, calling this command list files. So we can do list files, list me all the files that are in the data folder, and there indeed we have this topo change.zip. So I'll comment that out, but list files in the data directory, and I'll comment this out because I don't want to run it again. So now you'll notice that this is a zip. This is a zipped up file, so we don't actually want it to be zipped. So let's do $unzip. That's a function to unzip zipped files. So that's exactly what we want. Here we're going to point to the zip file, which will be data /topo change, which is what we just downloaded. And then we also want to give it an exit directory. So where's it going to go while it's being unzipped? So we'll do unzip the data set. So we'll do unzip data topo change.zip, and the xdir is going to be data, and then I'm just going to make a new folder called topo change. So this will be a folder that contains all those files. And now again, let's just take a look at what we unzipped. We'll go, now we're not going to just look in data to list the files, we're going to look in this topo change folder. And here we see we have essentially all the files for a typical shape file. So you have the main file, this topo change polygons.shape, and then you have projection information, database information, and other things that you might want to have. So that works. And again, I'm going to comment this out because I don't want it in the code. Since I already downloaded this file, I'm going to change this chunk to be eval equals false. And what that eval equals false is going to do is it's going to say, hey, next time you run this, don't run any of this script because we've already created this path, we've already downloaded this file, and we've already unzipped it. When you are working with this, you're going to have to run this code yourself first, just once, and then afterwards when you knit the document, it will ignore this code chunk, which is nice. Okay, so let's check out the data. I just hit Control-Alt-I. And okay, so I just said we have this topo change polygons.shape. Well, how do we read in a shape file? So let's go ahead and make an object called topo change, and we're just going to use this function from SF called stRead, and it's in the data folder topo change /topo change polygons.shape. All right. I didn't run my first chunk. So we'll rerun that because I didn't load any of those packages, which means it can't read it. You'll notice all of this stuff was base R because it didn't rely on any of these packages. And now when I run stRead, it's going to read in that data set. And when you read it in, you can see that it's 8,958 observations of 52 variables. And so we don't necessarily want to look at every single site, but let's go ahead and check out what are the column, what kind of information does this shapefile hold in its columns. So we have something called area, perimeter, number of pixels, NED min, NED max. So these are sort of summarizing a bunch of information. I can tell by the all caps this was probably done in ArcGIS. That's a typical way that things are sort of made in ArcGIS. Let's go ahead and maybe like, we'll just say check out the column names, which I will then comment out. let's maybe look at what let's do a summary of topo change and then area. Let's see what area looks like. Okay, so we have a bunch of different areas. I think square kilometers is maybe the easiest for me to interpret. So let's do summary area square kilometers. So some of them are less than a square kilometer. The mean is 0.15 of square kilometer, and the max is 9 or 10 square kilometers. So that's a pretty big mine or urbanization project that moved a lot of earth. And for the purposes of this class, let's just say we want to keep only the top 10 biggest mines. So let's just say biggest area. And then we'll do topo change. And here we're going to arrange in descending order the entire data set by area square kilometers. And then we're going to slice and just keep the top 10. So let's go ahead and do that. Okay, so now we have these 10 biggest areas. I'm going to rename that just 10. I can't do that. Biggest area. Whatever, we'll just keep it as biggest area. And then I'm going to go ahead and do a map view of biggest area. Sorry, you can't see me typing. Map view biggest area. And it's going to plot 10 polygons. And you can see, since we don't really know exactly where they are, you can't quite see them, but you can see these tiny vague dots. So if you zoom in way down here to this one that's called 7 and it's in Arizona, we can see it has this big of an area. I think that's probably in square meters. And then you can see it in square kilometers. So it's 7 square kilometers. The quad name will be the quadrangle or the sort of corner of the larger USGS map. So this is a name we'll want to keep later. So let's just go ahead and explore what this mine in Arizona looks like. We could obviously pick other ones. Looks like there's a big mine in Nevada. There's one outside of Salt Lake City. There's probably some up in Minnesota. These are iron mines, I would guess. We can sort of look at the imagery too if we want to see what these mines look like. Oh yeah, they're definitely big. It looks like they're bigger than the ability for SRTM to detect it. These are big old surface mines. So we'll sort of just let's double check what the Arizona one looks like, and if it looks good, that can be the one that we focus on. And by good, I mean just kind of interesting. Like it has had a lot of topographic change. Oh yeah, it's a big old pit. Great. So now we have a sort of focus mine that we're going to take a look at. We can subset this mine in a bunch of different ways. I'm going to keep that map view. Apologies. Map all mines. And then, I don't know why my computer does that occasionally. We'll say check out mine in Arizona. So here we can subset this. We're just kind of going to look for a specific ID. I don't see an ID column in here necessarily. We have a land use coverage class, quad name. You know what? We can just subset by using this quad name. So I'm going to go ahead and copy that. And I'm going to say AZ mine. And I'm going to do topo change filter quad name equals that name we just did. It looks like it added a space. That's what that little dot is. I'm going to delete that and hope this works. I'll run that line. We have more than one. Okay, never mind. So I tried to go back to the original data set, but there's probably adjacent. You can see there's adjacent mines that are also pretty big. So instead of saying topo change, I'm going to switch this to biggest area. And rather than getting 6 this time, we should just get 1. Yeah, and we did. Okay, so now we have our one Arizona mine. Let's just quickly map it to make sure it's indeed the same one we think we're working with. Okay, looks the same to me. Yep, it's that big pit mine. Great. Okay, so all this so far has been spatial analysis, right? We haven't really messed with raster data set yet. And that's because we haven't had any raster data. So to get the raster data, I'm actually going to add that map view back in. We're going to use the elevator package. frankly, I totally forget the command. I think it's, actually I don't. It's get elif data. Get elif raster. So if we go to get elif raster, it says locations, and it's either a data frame of long and lats or a spatial object. So it can be a spatial object, which is azmine is a spatial object. So that's good to know. So it looks like we can use just that, and it'll download all the elevation data around this object that's in our viewer. So basically it'll download all the elevation data that touches this. Let's go back to the help. Z, so the zoom level to return. The zoom range is from 1 to 14. Okay, what does that mean? I'm guessing that basically, I'm not guessing, I know this. 14 is going to be a really high resolution raster, so that's going to mean that the dimensions of the raster, rasters are almost always squares, so you have basically at a really fine scale, you might have a 1 meter by 1 meter raster. This is where from space you could actually identify individuals on Earth. If you had a bigger raster, you might have like 10 meter by 10 meter where things and images start to get fuzzed out. So 14 will be the highest resolution possible, and then 1 would be the lowest resolution possible. Earlier I said that Elevator gets its data from the NED. It does get its data from the NED, but it also gets its data from all kinds of other sources, and that is all documented in this MapZen documentation here. So MapZen is a global map that's the best available elevation data set for anywhere in the world. Okay, so we'll go back to R. We sort of have learned what this elif raster data set means. We'll say AZ raster. We're going to directly download it from the server. So we'll go AZ raster, get elif raster, and we're going to say the locations is the AZ mine. And for the Z level, let's just go ahead and say 12. Let's see what that does. If the download takes too long, I might make it 11. Hopefully it's fairly fast, so let's just say that. We'll run the line. It's going to download the DM. It took very little time. It's very fast. What it's doing here, it's telling you what it's doing. It's merging multiple sources of the DM. It's re-projecting the DM to the original projection. And by the original projection, it means the AZ mine. So we can run this command, check the projection of AZ mine to see what that should be. And the command is called stcrs, AZ mine. And so that's going to give us this projection that came down in, which it says that there's no PSG code, which is means it's going to be slightly harder to work with because there's no shortcut, but it does have a projection information in here. It's in NAD83, it looks like. And so that's what that raster data is going to come down as. So that's good to know. I'm going to just comment this out. I always do that. Projection. And now we have this thing called AZ raster. So if we look at AZ raster with the structure command, str AZ raster, you get a bunch of information here, but at the very top of that, you get a formal class raster layer from the package raster with 12 slots. So basically, there's 12 different ways that data can be stored. We can also look at the structure in a different way. I'm going to comment that out since I don't want to run it again. We can do summary of the data. We can do a summary of AZ raster. What that's going to do is sort of say, give us a summary of the values in the raster. So basically, there's a ton of NAs in this data set. The max elevation is 1,484 meters, and the min is 856 meters. Okay, that's useful. But what does it mean to have all these NAs? Well, finally, we're going to just go ahead and call the command plot. And we're going to plot AZ raster. And we're just going to use the base plot here. This is what comes with R. And this is sort of what that data set looks like, where the white is the low elevation and the green is the higher elevation. And so that's sort of our first look at this raster data set. It's pretty zoomed out. You can see maybe why it's projected in a slightly different way. So the coordinates sort of turned because it went into a local projection. You'll also notice in this plot that it doesn't really look like there's evidence of a mine here. So maybe this Arizona raster we downloaded is actually the original raster. So this is the sort of elevation profile before mining. So why don't we just call this before, AZ raster before. And we can just really download the data because it's pretty fast. And then now we'll have to change this code, and we'll just say AZ Raster before. And it does give you this useful little note that you know elevation units are in meters, so that's useful. And it just tells you the coordinate reference system. Okay, so now we have the sort of the data set, and we're gonna, this is the sort of pre-mining, but why don't we see what the post-mining elevation looks like? I'm gonna say up here, download pre-mining DM. That's fine, I didn't mean to run that. And then so now we need to use a different data source to download the post-mining DM. So let's go ahead and do that. There's this function in Raster called get data. So this get geographic data, it's in the package Raster in library dar. And basically what it says is get data, and then you give it a name, and then do you want to download it, and then you tell it where to go. And when we use get data, we can download stuff by a whole country. So this is like getting data for the whole country. We can download SRTM data. This is the shuttle radar topography mission data. And that's the data that we want to use. That's what the USGS was comparing. And you'll notice it just takes a long and a lat argument. So maybe we can go back to our viewer and try to see if we can get lat and long in here. I don't actually see that we can. So how can we find out how to do that? Let's go back to the help. Long, it only takes long and lat, it looks like. So we'll say SRTM. And this one, unlike the get elv raster, what it does is it downloads the data and stores it somewhere, and then you have to read it in. So we'll use get data, and it'll just be its own line. So we'll do get data. We want it to be SRTM. And then we want to put in a long and a lat. Let's see if we can find out where. One way to look for the longs and lats is to just look at the geometry of this data set. Does it really look like what I want? Nope. Took me a second to remember, but there's another command we can use to get the long and lat of this document, and so it will of the original map. So if we look here, this has some center piece, and that can be our long and lat. So what we're going to do is say center, AZ center, and we'll do ST centroid, and what that's going to do is extract the centroid of that object. So we'll do of AZ mine. And then it's giving us a warning that says its attributes are constant over geometries of X, because it's keeping all these attributes, which is the sort of columns, which we don't care about for this particular use. So we'll do AZ center. That's the map that just showed up when I paused the recording. So that's now the center of that mine. Great. And then, so let's say extract centroid of mine polygon. And then we will map it to check. And then there's another command, get the coordinates, called st coordinates. And we'll do that of this centroid now. And so we have an x and a y. Unfortunately, that's in meters, so that sort of doesn't quite work for what we want, because we want it to be in decimal, because that's what it looks like if we go back to the help. Of get data. Okay, it's easier to do it from here. Then we get we can see that the get data SRTM has a long, that's just a simple number. It's not one of these big numbers. So what we'll have to do is transform this, probably do a global projection, since this, you can download SRTM data anywhere. So we'll use the 4326. And then we'll map it to, again, double check it makes sense. Now we'll get the SD coordinates. Okay, and now we have the long equals negative 11.0417. And I'm just looking at the bottom here and printing that out. And the y equals 31.8414. So that's one way to do it, is to write them out custom like this. Another thing we could do is say, we can make this an object. So now we have this object called chords, and it holds an x and a y. And so the long, I have to think this through every time. The long is the x. So we'll do chords x, and we'll see if I'm wrong. So now we're just calling that very first thing called x, and then we'll do chords y. And that's just to avoid handwriting this down. You might make mistakes. You might change where you're downloading this data from. So it's just sort of a way to avoid those mistakes. And then I'm just going to go back to the help, because I think there's a way to say the path. So we want to point out where this will go. So this is the download path. So we'll say path equals data raster. And actually, you know what? I don't think it'll go into raster because we don't have a raster data set yet. So we're just going to go files, data. It'll just live up here. So let's see if that works. Y equals chords y. Oh, that's because that should be lat. Oh, and this is not a data frame, so it can't be subsetted that way. So that's why it's giving that error. This error in chords x, the $ is invalid for atomic vectors. So instead, I want to do chords 1. So the index of that is always going to be long than lat, it looks like. So then chords 2. And let's see now if that works. Great. So now it's downloading this file. It's going into the data folder. And we're just waiting for it to download. Great. It downloaded it, and then it added it here. And it's a TIFF, and then some affiliated things. But TIFF is a very common raster file. So now we're going to have to read in the data. I'm going to, since this, again, is another dynamic download, we don't need to rerun this. So we'll just do eval equals false. Once you've run this once, the data is here. And so you should be able to just run this chunk once, and then we don't want to rerun it again. Add another column, which is read in SRTM data. And so now we have this data set called SRTM 1406. The 1406, I'm guessing, is a tile, but we'll call it AZ raster after. And we'll do the raster command now. So we're going to directly read this using the raster command. And that just is exactly like stread or read underscore CSV. You just give it a path. So we're going to go data / SRTM 14_06.tiff. And now we have this thing called AZ raster after. And let's go ahead and plot it to see what it looks like. Okay, so now what we downloaded was a whole tile, and what we can see from downloading that tile is that we're getting a far, far bigger area of data, because what it did is downloaded a very large area. So now we're going to start to get into sort of raster operations. But at least we have the data read in, and now what we want to do is clip this to the much smaller area of the AZ raster before, so we can actually compare them. Clip SRTM data to NED data. So now what we want to do is clip these data sets. When you're clipping or doing anything with raster data sets, it can really slow down your computer. So this is a lot of data in this plot. And so there's two ways we could clip this data. One is to reproject this raster into the same kind of format as the other raster. But since this is a much, much bigger data set, that's going to take a lot of time. So instead, we're going to reproject the smaller raster to look exactly like this raster. And we can sort of look at the structure of these rasters by looking at the summary information. So this is the elevation. This is where we know it's going to a much larger area. There are 0 NAs also in this one, which means that the tile is completely full. There's data in every cell. We can also do, I think there's a resolution command. Yeah, res. So we can do az raster after, and then res az raster before. And what we can see is these are doing things in a very different way. So 16 is probably 16 meters resolution. 0.000833333 is probably a decimal degree. So these are different shapes of raster, and so we need to make sure that they're the same. So let's go ahead and say check resolution of rasters. I'm going to comment these out because we won't run it again. And then we can also do a projection. We can check the projection of these. So AG raster after. Okay, so that's in WGS84, which indeed is decimal degrees, and AZ raster before. Oh, gotta spell things right. So that's in this NAD83 definition. So we're gonna just go ahead and say check projection. So basically the projections don't match up, which means we can't do any spatial operations on these things until they do. So let's go ahead and change AZ raster before reproj. And we'll do project raster. Oh. I think this is going to make it bigger than I want it to. Let's see, this might not work. AZ raster before. I want to project that from AZ raster before to AZ raster after. So now it's just changing the projection. Okay, that didn't take too long. And if we plot it, it's probably because I spelled something wrong. Reproj. Reproj is what I want it to be called. Reprojected. And now we can plot it, and you can see it's in a tiny little section, and that's because it basically, that is the same size as the area, but we're only zoomed in. This is this little tiny pink area is where we actually want to be looking at the data. So what we can do is go ahead and remove the NAs in this one, so it'll clip way down to that small size. So we'll do, forget how, remove. I think there's like a trim function. So let's go ahead and look at this function called trim. Trim or shrink a raster object by removing outer rows and columns that all have the same value, such as NA. Great. So we'll say AZ raster trim before trim. We'll do trim AZ raster before reproj. And then we'll do plot of that. Great, now we finally are back down to that first image we saw, and we just have one more step. We want to clip the after data set to be over the same area. So we'll do AZ raster after clip, and we'll do this function, it's just called clip. Maybe it's not called clip, it's called crop. Let's check. Crop in package raster. So we're going to crop AZ raster after to AZ raster before trim. And now when we plot that, we can see, and now we actually start to see that mine. If you look up in the top left, this like incursion in here of low elevation, if we toggle between these two, you can see they're different. So you can see that this like square area has been dug deeper, and I'm guessing that that is where the mine is. Okay. Just going to clean this up a little bit. Plot clip data set. Just trimming the white space, and then this is reproject. Small raster to larger raster projection. Okay, and now finally we can do what we came here to do, which is to go ahead and take the difference between these two rasters. And this is where it's really nice to be working with the raster package, because to take the difference, we can call it a DEM diff. All we do is say AZ raster after clip. So this is the after. Actually, it's probably best to do before. So I'm going to say before. Because before minus after, that way if there's a positive gain in elevation, it'll be a positive number. And if there's a lowering in elevation, it'll be a negative number. So we'll do AZ raster before trim minus AZ raster after clip. And what it's going to do with this, again, raster data set, so spatial, is it's going to go every single cell, it's just going to subtract what's in the other cell. So we'll run that, and then now we can plot the DEM diff, and everything should show us where this mine is, and great. All the green is essentially zeroed around areas where there's very little change, and then this yellow is showing areas where they've actually decreased the elevation by 60 meters. So it looks like that's where they're really digging out this pit. And it also looks like where they're digging it out, they're not necessarily putting the rocks right back in the same place. Because if they were doing that, you would see a positive increase in elevation. So that's cool. Let's go ahead and comment this, take the elevation difference. And I think that's where I'll stop today. In class, we'll sort of do some more complex operations and change the geometry and try to figure out where that dirt is going. But hopefully this was fairly clear.